To migrate to the Radiance configuration, we need to only remove the fibre, bundle and diffuser from the entrance port of the IDR300 and proceed to install the components for the Radiance measurement. We typically site the TEL309 on top of the IDR300 simply due to the length of the fibre bundle as explained previously. This is quite convenient. The TEL309 should be connected to USB of the computer, and the power supply of the TEL309 should also be connected with the rounded face upwards. We have already installed the fibre to the TEL309 and need to attach the fibre to the IDR300. But again, we should, in this case, initialize the system previous to fitting the fibre. I have positioned the SRS-12 calibration standard on a pair of lab jacks to obtain the approximate height of the TEL309 and have connected it to the 605 constant current power supply. Set to 8.5 amps, with the key slightly retracted, I can now power the source on. And then there is light. We will pass in a moment to the software to look at the alignment of the TEL309 to the source. I would use an alignment aid such as a business card at the plane of the SRS-12. We will set the TEL309 through software to image a plane 200 millimeters distant. And if we place the business card on the front face of the SRS-12, we should adjust the position of the SRS-12 to get the aid in focus. In this manner, we don't actually measure the 200 millimeters distance, but rely upon the calibration of the TEL309 to do so. This is particularly convenient when you cannot access the apparent source location, or a source is recessed within a housing and you cannot place the alignment aid at the source, for example. We will now initialize the software, then fit the fibre bundle in position. We will now run Bowman Plus in the Radiance configuration, making sure, of course, that the IDR300 and the TEL309 are connected to USB and both powered on, otherwise error will be reported. And we hear first the monochromator initializing, and then second the TEL309 initializing as the stages within the TEL309, which moves the periscope, lens system, and the aperture wheel returns to a reference park position. At the end of this procedure, we can fit the FOP-UV bundle to the IDR300, and then we can go to utilities TEL309 to look at the TEL309 view to align the TEL309 to the SRS-12. So now the system is parked and we can attach in a very short moment the IDR fibre bundle. Now the system has initialized and we can fit the fibre bundle to the entrance port of the IDR300, and we can go to utilities TEL309. This utility gives a view of the CMOS camera on board the TEL309 and allows setting the measurement distance, here 200 millimeters. We must make sure that the close-up lens is in place and we hit OK. And the periscope of the TEL309 will ensure that the TEL309 is looking at a plane 200 millimeter distant. It's worth noting that in the TEL309, light instant on the aperture wheel Some will pass through the aperture selected, the remainder is reflected and collected onto the CMOS camera for purposes of viewing the scene that we are measuring. So when we have reached this location, we will see the aperture wheel rotate and the crosshair will come into view for the purposes of alignment. Clearly, with the crosshair in place, no light is transmitted to the monochromator. Later we will use optical alignment by signal to help align the source as well as this visual alignment. Now if I place my alignment aid at the SRS-12 and I adjust the position of the SRS-12, the distance of the SRS-12 from the TEL-39, I can see that I am now at a distance at which the source is in the plane of the SRS-12 is in focus. And it's also useful just to use, for example, an Allen key and pass it in front of the window of the SRS-12 to get an idea of the alignment of the SRS-12 in terms of the height and the lateral position with respect to the TEL-39. The TEL-39 is looking effectively at a 2.2 millimeter diameter area at 200 millimeters and 11 milliradians field of view, so it need not be entirely central to the SRS-12, but certainly in the vicinity is better. And indeed, in any case, the TEL-39 shouldn't be seeing anywhere near the edges of the SRS-12, where the view may be impeded by the outer walls of the window. So we'll just adjust the position again and focus, and then I'll just pass the Allen key and I see a fairly central position of the SRS-12, and you can see the Allen key is quite well in focus there. This procedure using the Allen key will also allow one to appreciate quite what a small area is being measured. One can adjust the focus of the TEL-39, but in most instances I recommend you set to view a given distance and then you adjust the position of the source to obtain the focus. The settings of the camera need only be left on auto. We can access through the aperture wheel here, part here, the selection of the 1.7 or 11 milliradians with the selection or not of the high radiance mode. In the high radiance mode, we migrate from photomultiplier to silicon photodiode at 400 nanometers. This is recommended really for the measurement of white phosphor conversion LEDs, in which case the peak emission will overload the photomultiplier in the vicinity of 450 nanometers, for example. So moving to the silicon before 450 nanometers will result in a successful measurement. If we select for now the high radiance mode and apply, we can see the black area is where light is transmitted to the monochromator, and the view of the camera is around 11 milliradians, so we see very little more, as opposed to the 1.7 milliradians where we see rather more of the scene. So for now we'll set 11 milliradians. Down the bottom here is a alignment utility, much as we have aligned sources using the irradiance setup. But for this SRS-12, a large uniform source, there's no need to align finely at all. So we can close this utility and go to scan setup. Now we should load a custom wavelength file from the custom wavelength files folder, radiance 11 milliradians. We can launch a number of scans. We'll select here 10 scans and we can hit new scan, and showing that of course an advanced data correction is not selected. And at the end of these measurements we can come back and look at the results and apply data correction. Now we have reached the end of this measurement. We can see in this high radiance 11 milliradians mode we change from photomultiplier to silicon photodiode at 400 nanometers. We see more detail on a logarithmic scale, and we can see the 1380 nanometer absorption of the quartz fiber, which even at this short cable length does attenuate very significantly the signal. In most cases this is a no problem, since most instances one is measuring LED sources for which there is no emission in this region. Again, we can apply the procedure of deleting the initial 5 spectra, saying that's the lamp warm-up time, and then taking an average of the remainder. And we can delete the initial measurement results and to leave only the average. If one wants to keep the original data, one can of course save the file to allow you to saving all of the original data, and then generate, having deleted the first 5, save a new file calling it the average, for example. In any case, we need to take the average to apply the data correction procedure. Scan data correction. Certificate file is that of the SRS12. This has been selected once and will always be selected in this configuration. System file is the average measurement of the 11 milliradians field of view. Calculate. Data correction not selected, yes, and we save to file. Radiance 11 milliradians in the calibration folder. Radiance 11 milliradians high. It's most convenient to calibrate also the 1.7 milliradians field of view at the same time. The reason for this, of course, is that you calibrate in 11 milliradians, then we will measure the source under test. If the source under test fails the risk group 1 classification, we need to measure in 1.7 milliradians, and it will be most inconvenient to have to remove the lamp under test, to recalibrate, and have to realign the lamp under test. So typically, running batches of measurements at a time, I would recommend to calibrate in 1.7 milliradians field of view as well as 11 milliradians field of view. A note: in the 1.7 milliradians field of view, having selected 1.7 milliradians through the TAL39 utility, we should go to custom wavelength files and select the 1.7 milliradians field of view custom wavelength file. Please note that the difference between the two is that whilst the 11 milliradians file steps from 300 to 400 in 2 nanometer steps, then 5 nanometers thereafter to 1400 nanometers, the 1.7 milliradians file maintains the 2 nanometer step to 480 nanometers, and then thereafter 5 nanometer steps to 1400. The reason for this is that whilst the 11 milliradian field of view has the option of the high radiance mode, where signal level may be high, the 1.7 milliradian field of view does not have this option, since the signal level in calibration would be impossibly low. We still then use the photomultiplier for the full range to 850 nanometers, but to get past the region of the 450 nanometer LED of a phosphor conversion LED, we step at 2 nanometers to 480 nanometers rather than 5 nanometers from 400 nanometers. In this manner, we attenuate the signal and hope that we will have a successful measurement, and in most cases this will obtain. So we can go and generate, based on data I've previously measured, the calibration file for the 1.7 milliradian field of view, which we calculate and save. In this manner, one can simply, as required, go into the data correction page and load from file the required calibration file. The first measurement we will do now of the source under test is the 11 milliradians field of view, so we will select that calibration file. As a note, with regards to selection of high or not selection of high radiance mode in the 11 milliradian field of view Well, this is quite a loose definition, but the luminance of the SRS-12 is around 29,000 candelas per meter squared. Not far, in fact, from the 10,000 candelas per meter squared that IEC 62471 presumes as being the level at which no measurements are required, and based on the fact that it is a comfortable source to view. If the source is not comfortable to view, we expect the signal level to be higher than that of the SRS-12 in this region, of course depending upon the source, and as such recommend using the high radiance field of view. For any source which is comfortable to view, then one would recommend using the normal, the not high radiance mode. Otherwise, if you use the high radiance mode and the source has very little optical output, the silicon detector, which is a low response, simply doesn't detect a signal, and you will probably, in which case, see gaps in the measured result of zeros. Effectively, no signal is recorded, in which case the measurement needs to be repeated. We will now look at setting up the MR16 lamp to measure and proceed with its measurement. We are now ready to measure the source under test. Here the MR16 lamp in the 11 milliradians field of view in the first case to evaluate for risk group 1 of blue light hazard and exempt and risk group 1 of the retinal thermal hazard. I've set the approximate height and position using these lab jacks to obtain the height of the telescope. I'm sure you will find a more suitable manner of doing so. This is a coarse alignment. The fine alignment will be done with the TEL-309 utility. One final point is that it's most useful to use the 7mm aperture provided with the TEL-309, placing it at the entrance lens to attenuate where required the signal on the CMOS camera, which may in other cases be in saturation and no visual alignment can be performed. One must, however, of course, remember to remove this prior to measurement, since otherwise the calibration would be invalid. We will now look at the alignment utility in the TEL-309 utility. Now we have set up the MR16 for measurement. One final check to the important point that we've loaded the correct 11 milliradians high correction file, data calibration file, and in scan setup we load, or make sure we load, the 11 milliradians custom wavelength file. We can now go to the TEL-309 utility, and in terms of the use of the utility to perform an alignment of the source, if we go to 11 milliradians, our target measurement field of view, we see nothing. Whilst at the same time, if we go to the crosshair, we can see the entire source, but no light gets transmitted to the monochromator. So I tend to use, in the first instance, the 1.7 milliradians field of view. So we have some visual return of the scene of measurement, and if we select a wavelength at which the source emits light, in this equivalent of the alignment DLL, and when the monochromator has arrived, hit monitor signal, we will see a report of the signal measured by the system. Now we go to the system, and we need the screen close to the vicinity of the measurement bench. Now we need to adjust the position of the source to try and obtain the alignment. In the case of this MR16 LED source, we know that what the eye would image is the diffuser, so we don't really expect to see anything which makes very much sense, given of course that we're looking here at an overall view of some 2.2 millimeters diameter. We are really zooming in on the fine detail of the source structure. And as one moves the source back and forward, one can get some impression of it being out of focus, a surface coming into focus there and moving out of focus. So clearly this vicinity is the plane in which we should measure. It's merely a question of finding the peak signal. And as we scan around we can get an impression of quite what we're looking at. Here we have a source which has 4 LEDs and associated lensing diffuser, so we should to some degree see that on screen as we turn the lab jack through the measurement plane, and we simply try to find a maximum. Essentially this is clearly a very difficult measurement to perform, subject potentially to significant error, but this is the nature of the measurement. Certainly one of the most difficult measurements that I have encountered in terms of accurate measurement results. So far I have tried to scan around with samples such as these. It really is relatively unclear as to what one is measuring, because there's nothing of interest that you can really focus upon and have an idea of where you're measuring. Again, using the trick with the tool, the Allen key, I can have an impression of where I'm measuring. I can see now I'm measuring I have a cluster of 4 LEDs, and I'm looking at the lower of the 4, actually somewhere fairly central to the LED package. I will just move around a small amount in this vicinity to see if we get a higher signal, and if not, I will try to optimize in this location and thereby perform the measurement. Again, we're looking for a maximum. One has to have an eye to the variation, and we don't need to be, or it's almost impossible to be absolutely at the maximum of the source. So I have a maximum of 1323, and I will try to aim for that in this difficult procedure, and I will, for the purposes here, settle where best we can find a signal without further ado. In fact, the final step, we're near the 1323 max we've seen, the final step is really to select the 11 milliradians field of view, ensure high radiance is selected because we calibrated in that mode, and we should, if we were able to move the source around a little bit to optimize the alignment, you can see actually that the signal has gone down because now we're using the silicon photodiode, not the photomultiplier, in the 11 milliradian field of view as opposed to the 1.7 milliradian field of view. Given that, for example, my setup is not the most stable, I really don't want to move the sample because I'm not confident that the sample will not go completely out of alignment. So I will remain in this position, close, and perform a single measurement with data correction applied as required. And now we see radiance in milliwatts per steradian per meter squared per nanometer on the y-axis, and we're measuring absolute radiance of the source. One small point that I didn't allude to in the previous measurements, whereas spectral check and the radiance measurement are very directional, taking light from a very small region of the source, the irradiance measurement, due to the cosine response of the diffuser, sees light from the entire hemisphere above. In the irradiance measurement, the room lights must absolutely be switched off, otherwise these will be measured and you will see, for example, peaks of the fluorescent emission, the mercury emission from a fluorescent tube in the measurement result. In the radiance measurements, the only way that any ambient light can be coupled into the telescope is if it bounces off the front surface or the surface of the source and down the optical axis to the telescoping lens, and similarly in a sense with the spectral check measurement. So there is less need to switch the room lights off, although it is a very good practice to do so. So we will look at the results when they come in, and after this we will look briefly at a another source, the LED torch that we've looked at previously with the PSL profiler, because in this case we will see much more clearly what the TEL39 is viewing. Now the measurement has finished, we have the results of the source. We can save this in the Spectra folder, radiance 11 milliradians of the MR16, and we have a successful measurement there. Again, you need not concern yourself with the integrals here, but I know that the limit of the blue light hazard risk group 1 is 10,000 watts per steradian per meter squared, and here we have 1,800, so we are below the limits of the risk group 1 limit, and therefore the source is classified risk group 1, and we need no longer do any more measurements of the source in irradiance. That is to say, we don't need to perform the measurement in an 1.7 milliradians field of view. And out of note, we can look at the luminance of the source. Well, 2 mega candelas per meter squared. That's quite a bright source to look at. It's worthy to note, so clearly this source is a high luminance, but this particular case of a 405 nanometer pumped phosphor as a white LED is quite interesting, since rather than using the typical 450 nanometer LED, which is in the central region of the blue light hazard function, the 405 is rather further out, which is why we have such a low blue light radiance. Interestingly, as I discussed in presentations elsewhere, if you consider the aphakic eye, for example that of children for whom the lens has not developed yet UV blocking properties, we will find that this aphakic radiance would be very much higher. The standards do not currently account for that fact. Before we leave the radiance configuration, we will look at another example using the TEL39 utility. Going into the TEL39 utility, we will look this time at the torch which we have previously considered using the PSL profiler. In this case, we can clearly see the LED chip, so what we see, or what we will see on the screen here, will be something that can be recognizable compared to what we have just measured with the MR16 lamp. For the purposes of alignment, we select 1.7 milliradians field of view, and we ensure we target wavelength of 555 nanometers, or an appropriate wavelength is selected. And we should reset the maximum for this measurement. The first key is that when you're moving a sample, trying to align a sample, so here the torch on my LabJack system, you should move large amounts at a time rather than get stuck in local minima in order to explore the measurement space. And you start to see features which give a clue as to what one is measuring. So for example, here we're looking at some feature, I think, on the front metalwork of the source. You can see there the arc indicating that the source must be to the upper left somewhere, so we can duly move in that direction. If one starts far away from the TEL39 and one moves in, one tends to find that one images, for example, I think I'm imaging the front metalwork of the torch, and as I move further in, I'm actually in the vicinity of the LED, so we're quite well aligned already, but not in focus. Clearly the signal level is an overload, so we should place the aperture before the lens of the TEL39 to reduce the signal. The pulsing we're seeing there is an aliasing between the PWM of the torch and the TEL39 camera, which is rather annoying. Now, because we've placed the aperture in place, we should reset the max, because we will never find that max with the aperture in place, and continue to adjust the focus. We can see some feature, some graininess in the view, and I think that is the lens of the torch. So we need to move the torch closer to the TEL39, and we start, yes, here to see the LED chip and there the wire bond to the upper of the screen on the LED chip. You can see the electronic distribution grid around the LED chip, but still it's not entirely clear where one obtains a focus, and one moves further and forward and further back trying to optimize the focus. Essentially what we're looking at is a diffuse source, so there are very little features to focus on. Now it's all well aligning for a maximum signal at 1.7 milliradian field of view, but one must also take into account that what we want to measure now is an 11 milliradian field of view. So we should be in a location where when we select the 11 milliradian field of view, we see the chip over the full field of view. We shouldn't have the 1.7 milliradian field of view to an edge of the chip, such that when we select the 11 milliradian field of view will see dark to the side, which would be entirely incorrect. So having selected a appropriate location, we select 11 milliradians and perform our measurement. And just to note that these spectacular images one finds in the 11 milliradians field of view in particular is merely a result of the optics in the telemetry 9 and the light source we're injecting in there, and is not a problem in its operation.